Hello, hello. I think it's time to get started. Let's let's start the morning paper presentation session. In this session, we have 5 papers to be presented, and each will take 15 minutes, including 2 to 3 minutes question and answer. Okay, is the speaker for the first paper here? Great. Great. Could you please briefly introduce yourself?
Sorry?
Can you briefly introduce yourself?
Right, good morning everybody. My name's Andrew Losty. I'm at UCL. I finished work after quite a long time in industry and decided to go down the PhD path. So I've just completed, well, I'm in my second year now, and sort of enjoying the PhD process and path. So if I can give you my talk on matter. So it's really matter in relation to... Great. Yeah, so I'd like to do explain to you as to what I've been doing on matter and really looking how the security framework aligns with international and national standards. So really, the outline of the session is just, so I've done this brief paper. It's an in-progress work. So what I'm going to look today at is really why I think things are changing and the scope of change. A little brief overview of matter, which I'm sure many of you know and maybe know better than I do. So I'd be very welcome to discussion points. A quick overview of the research and the conclusions. So this is something we all know, but obviously the IoT is known, generally as the Wild West in terms of computing, security, privacy. And so clearly moving from a platform of isolated ecosystems in great competition, fast change, rapid development, where there's a great deal of rush to get a product out to market, and really high levels of product differentiation. So all that causes the problems which we're used to, and that's isolated, incompatible systems. The need for multiple management platforms and applications. Manufacturers having to build lots of different models. So that's what we've all been used to, and what we're saying really is that matter wants to, and it seems to be doing quite a good job of changing that design and that method of IoT development and production. So rather than competitive actions, it's a collaborative action. And 350 manufacturers, 3,856 at the last count that I looked, certified devices. And that's a rapid change from when this working group was founded in 2019 to when the initial matter specification was released in 2022. So very fast. Now, clearly, the matter group has got the biggest technology providers in there, and that they've made the decision that collaboration in terms of development and the protocols is a lot safer economic bet than working individually. And so, but even though so what it sounds like, it's a very democratic process in the fact all these companies working together. The downside to this is that it really looks and feels that the bigger players are driving the protocol and the standard and the development. So to become a member of the CSA, to have your device certified and produced is $7,000 a year. So not the biggest figure, it's not the biggest hurdle. to become a member of the highest level of the Matter board, which dictates policy and drives future development, that's $105,000 a year. And clearly not many companies can afford that, and so then it plays into the hands of the larger players. So since Matter was launched, there's been four versions, and these are either updates to provide support for new devices, or they are fixes or a mixture of the both. So we can see from Matter 1.0, and the latest has been 1.4.2. So 4 major revisions. And what we've got to think about is that Matter for many devices is a purely software update. So Amazon, with one background software update, there was 100 million plus new Matter devices out on the market. With Apple, it was an update on iOS, either 15.1 or 16.1, depending on the platform type, brought them Matter support, and Google for speakers 1.56. And so huge numbers of devices suddenly became Matter capable. Protocol stack is either the top 2 layers of the TCP model or the top 4 layers of the OSI model, and it's all built on standards. So there's nothing there other than to say that the manufacturers really want this to be built on standards, which gives us a good degree of trust in the operation. Now, what I wanted to do was just to try and have a look at the Matter protocol and how it aligns with security standards, security standards. So that we'll see as to the chosen models. But I've got 6 domains that I want to look at first, and you can see as to what they are. Those 6 have not been picked on any absolute fixed policy because it's a means of assessment. So they seem to be fairly spread across the technical board. So these are the standards that I've gone for. So it's a mixture of international, US, European, and UK standards. They seem to be the most relevant standards to build a searchable domain, and it's a mixture of mandatory legislation, technical standards and specifications, foundation guidelines, and core IoT baselines. So those are the standards that I'm assessing Matter against. So the first one is device certification. So device certification, it was mentioned earlier that we've got some means of assessing products, putting them into classifications, and in this case, all Matter devices all commercial Matter devices must be certified. There are 32 test centers around the world, and this is a paid-for service paid by the manufacturer. And what we see really is that Matter aligns with the new Cyber Resilience Act, so that is in force now in Europe and will be fully in force at the end of 2027. So it's coming in stages, but that mandates certification for the higher classes of device, and so Matter does align with that, and that's quite interesting, so that the newest standard includes certification. We'll call them the more established standards don't. But it does raise quite a few questions in terms of what that brings to the IoT market. There's so some alignment, but only with the newest standards. And what we have, in my perception, is that we've got either certification schemes, which we've said Matter and the CRA, and you've got a number of label schemes around the world, so whether that's Singapore, Finland, Germany. So there's a lot of effort going in to try and classify devices, The fact is as to whether you make this absolutely mandatory. That's where the CSA and Matter have both said absolutely mandatory. So the attack surface minimization. Again, I wanted to see as to how does Matter align with sort of attack surface. Generally very good. So it limits all its communications to TCP 5540. So all communications are secure and encrypted, and it limits the protocols used. So it is a very much tight, really tight interface, and that's been done very well. And clearly, according to this chart of the standards, that aligns very, very well with the expectations and the international standards. What it doesn't do, though, because we've got to recognise when there's gaps, it advertises its services, and it does that as multicast, and it sends out these announcements, and it sends quite detailed information, giving the vendor ID, the product ID, the device name, the device type, and with this you can look up all details as to what the product is, get lots of background information, and this is done, it should be tighter controlled is the way that I'd see. So I think that Matter does control the interface in some ways, but in other ways it doesn't do this particularly well. Secure communication is very much what Matter is built on, so we'd be surprised if it wasn't, considering it's backed by all the major technology providers, and it's secured during the commission process with a password authentication session, and it's encrypted during normal operation with a certificate authenticated session. So very high levels of encryption, integrity, and replay correction, and it matches up well. So I think that that's a good thing on the Matter side. Software update support. I'm not looking here at the software update mechanism, and probably that's a good thing because Matter supports its own update mechanism, and it supports custom update mechanisms. So each product would be, to some extent, possibly different. What it does do, though, is that we're looking at some standards which declare that there must be a minimum update support period. So nobody wants the device, you've just bought it, you've installed 50 of these devices around a building, and then you find that there is no software support. As we've seen with some major devices, major manufacturers recently withdrawing support for IoT products. So that's one area which is not really covered by Matter. And the regularity of updates is actually one of the other questions. So there is no guidelines as to how frequently the devices will get an update, no guidelines as to how long they will get an update. And I did a little bit of lab work to check, and these are you can see these 18 devices. 3 of them have received software updates since their launch, and all the others, the 15 other devices, haven't. And so some of them are really running on version 1 of the specification, whereas very few of them are running at 1.4. So again, another point to say, is Matter really adhering to this? To these standards. Whoops. Logging and telemetry was something that I wanted to look at, and so clearly these are constrained devices. They cannot hold great amounts of logs, but to some extent, possibly it should be within a standard to say that they hold critical logs, that the device has been compromised or attempts to compromise them, and whilst Matter does build into the specification the means of logging and controlling the logs, so it supports the telemetry, supports crash, fault, network, lots of logging. What we see in real world is this is all down to the ecosystem. So if you put a Matter device onto a Home Assistant platform, you can see detailed logs historical logs, tremendously powerful in that way. You put the same device onto a Google platform, and Google you've got no logs. So it's highly, even though it's matter, it's highly ecosystem dependent. So I'm seeing that as not a match. Secure storage, really the matter should say yes here. So that's a failure of mine at the top. So matter absolutely wants to protect the keys and certificates that everything is based on, and it does do that without any question. The thing that I would sort of observe is that it doesn't specify how it's going to do it. It leaves that to the manufacturers. And what you'll see with a great point of our matter is that the specifications are published, the information is there, but the implementation information is down to the individual companies, and that is not published. And when asked in terms of technical questions going back to matter, then if it's not published, generally it is not permitted to discuss these points. So there's a bit of obfuscation of the information there. So in short, the device certification is, I think, a very good step forward, but it's limited to the matter-appointed 32 vendor centres. It's questionable as to what the focus is there, whether it's security, privacy, or whether it's interoperability. But they do publish the matter test scripts, and so there is an openness there. So I think that device certification is tremendously positive. The other thing I should have said is that certification information is written up to a blockchain database, and so that status is used when the device is commissioned. So it's a closed loop. It's a tremendously powerful system. Attack surface minimization, as I said, generally very good, apart from MDNS, which seems to advertise a lot more. And the reason it does that is that some manufacturers, you can adopt a device onto a Google platform. Later on, you might want to adopt the same device onto an Apple platform if there's two people in the same household. And so some manufacturers leave the device in almost a commissioning state so it can be adopted at a later time. So there is a reason behind it, but it seems a bit lax. Secure communications is really in line with the specifications. Software update support doesn't seem to match qualities, and the same with logging and telemetry. So there is a summary of results, and I plan to go on to more areas to fill out the gaps in this matter. So thank you very much for the opportunity of speaking to you.
Yeah, thanks so much for the speaker. I think we may not have time for the QA, but we do have the poster session following the presentation sessions. We can leave a question at that time. Right, thank you. Yeah, I think the second speaker is a PhD student from Dartmouth College. So.
Thank you. Good morning, everyone. My name is Ravi. I'm a PhD student, like the chair said, at Dartmouth College. And today, just like Andrew, I will also be talking about the Matter protocol. So a lot of work kind of revolves around the analysis of Matter. And what my talk aims to do is talk about some of the implementation. So Matter is becoming more pervasive. How, as we can researchers, use this in our experiments and so forth. So to concretely put it, I'll make two contributions. The first one is a guide for implementing new functionality in Matter devices, as well as how can we invoke the new functionality from a smart home controller. And to do this, to help you appreciate this, first I will give a short primer on Matter, kind of try to not make it as redundant since Andrew just did something similar. But then we'll also talk about the code changes needed from the perspective or from the device side. And then similarly, I'll give a short primer on how the controller works, followed by the code changes needed on the controller side. So what is Matter? It's an interoperability standard introduced by the CSA, I think around 2022. And it has gained support by industry. So what does this mean? So it means that you could have something like you have a TP-Link motion sensor, which could perhaps talk to a Samsung smart home controller. And then that might also talk to products from lesser known manufacturers. So it kind of promotes interoperability in that sense. So you're not really tied to vendor lock-in or vendor time. And you could use this with your smartphone, so your traditional iOS or Android device. And over the years, just like Andrew highlighted, Matter has gained support for new device types. And this means that it's becoming more pervasive. So I think Andrew also mentioned this, that you have Amazon supporting Matter devices. So now all of a sudden you have 100 million plus devices now supporting this protocol. And what this means is that, it's something that's interesting, it's becoming a bit, some might say ubiquitous, and how can we as researchers take advantage of this and might want to script our own experiments. So to kind of understand how Matter works, or some of the ensuing slides, I will first go through what the data model of Matter is. So this is kind of how functionality is grouped from the perspective of the device. So at the top level, we have the device. This is just essentially the entire physical entity. Then we have a node, so this is what a single Matter device is. Here I talk about a microwave oven, but something to better illustrate this point is if you're familiar with the HomePod, it has a speaker component to output audio, but I think the HomePod could also do temperature and that sort of thing. So the temperature component and the speaker component might be two different nodes. And then we have, under the node, we have endpoints, which is just a logical interface that groups a set of clusters. And clusters are a group of related commands and attributes. So typically in Matter cluster, the first cluster under endpoint 0 is used for administrative features like onboarding a device, giving access permissions, and that sort of thing. And then we have different commands under these clusters. So the commands are basically messages you send to the device asking it to perform some task. And then similarly, we have attributes, which are just pieces of information that you could ask the device to report. So you could use a command to manipulate an attribute. So what we're trying to do here is introduce a new command or a new cluster into the device. So we as a researcher are like, hey, maybe a Matter device doesn't have the functionality we want. So the motivating example we use here is to sanitize the device. And by sanitizing, I mean like not cleaning the device with like dish soap. I mean like if it has sensitive data, you want to scrape away from the device. For example, the device may collect telemetry data, and you might want to regularly wipe that from the device. Again, this is just a motivating example. You could use it for other purposes. And just for simplicity, our custom cluster just has one command, sanitize device. So to preface things, for this, I guess, instructions, we use the open source reference implementation of Matter. We implement this on a Raspberry Pi, but although physically it is a Raspberry Pi, logically to the smart home controller, it could appear as one of many different Matter device types. So for example, it could appear as a smart microwave oven to the smart home controller. And in theory, this should also work with any Linux system as well, but we tested just on a Pi. And one of the things we try to do is guide you through where you need to make these code changes. So I think if you do a clone of the open source repository, and if you do a recursive count of the different subdirectories, there are literally tens of thousands of subdirectories in the open source implementation. So we try to make things easier by telling you where you need to go and change certain files. So one of the first things you need to do is extend the data model. So you tell Matter that, hey, I'm adding this new cluster. And one of the first things you do here is you need to give it a code. So this is kind of similar to Mac OUIs. So there are certain codes restricted for certain vendors, but there are also a range of test values you use. Then obviously you need to give the cluster a name, followed by what are the capabilities of your cluster. So as mentioning before, we just have one command, which is sanitize device, and you need to give the cluster code. So these are important because they'll be referenced later on. And then once you've extended the data model to tell matter of your new capabilities of the new cluster, you basically now start doing the implementation. So it's typical C++ programming where matter uses the Ninja build system. So the first change you make is tell matter of include this custom cluster when compiling. And then, yeah, as mentioned, you have a header file, you do the class methods, and then you write your source. Here I just commented out the implementation code, but this could be whatever you want it to be. So you could have something like go through all directories, erase all the sensitive data. Again, this is just my case, but there may be other examples that you or other researchers might want to use. And it's important to adhere to some naming conventions. So we make sure like the naming is consistent and so forth. So once that's done, now we can attach the new cluster to the device. So then we use a GUI provided by Matter, which basically tells us we want to activate this custom cluster on a device. Here I'm just adding it to a microwave oven. And similarly, we could add it to a dishwasher or another Matter device. So the implementation code we wrote earlier is kind of agnostic to different device types. So what this means is, in theory, I use the same code and I can reuse it to, let's say, attach it to a smart microwave oven, a smart dishwasher, a smart thermostat, etc. And now all these Matter devices now have our custom functionality without having to write device-dependent code. So now I'll talk about the changes that are needed from the controller side. So we use Home Assistant. I'm sure many of you know about Home Assistant, but we use it because, one, it's popular. I think GitHub last year released a list of statistics, and it's like top 5 open source repository, and the metric being number of contributions. It's open source, so yeah, we could go ahead and tinker with it, which we as researchers love to do. And lastly, it has official support for Matter. So to kind of understand what comes next is we talk a bit about Home Assistant, how it works. So Home Assistant is released in a variety of ways. One of the simplest ways you could get running with Home Assistant is through what's called Home Assistant operating system. This is just a Linux Debian-based system. And it has one main component. So this is Home Assistant Core, which is really what the engine of the smart home controller is. And it has a Matter component which handles the Matter integration, and it also has UI components to handle user interactions, as the name suggests. But really what does the heavy lifting is something called the Python Matter server. So this is essentially just Python bindings for the Matter controller from the reference implementation. So we need to make code changes in all 3 places. So first I'll talk about what's needed in the server side, the core side, and then how we could create some sort of user interaction to interact with our new functionality. So similarly, first step we do is, again, tell the controller of our new server. So we make sure we keep the name the same, the commands, and importantly, we remember the codes or values we gave to the cluster and command ID from the XML file I talked about earlier. And then secondly, we do something very similar to the Home Assistant core. Again, it's just telling it of our new capability, adhering to some naming convention, and then telling Home Assistant that this new integration ties into Matter. Yeah. And finally, we do a UI component. Here, I'm just adding a simple button using a dashboard editor that Home Assistant provides, and just telling it what entity or what component this button should tie into. And finally, you'll end up with something like this, where you could have a button to interact with your custom functionality on your Matter device. So why is this useful? Like, why should you care about this? So remember that earlier image about having different devices in your smart home and interacting with each other. Now you could have your custom device in your smart home also interact with consumer off-the-shelf devices. And that might be useful to you as a researcher. Yeah, and that concludes my presentation.
Great. I think We have time for 1 or 2 questions. Great. Let me ask one question. Have you guys been able to, I think this is very interesting work. Have you guys been able to talk with the CSA or Meta community and see how this can be potentially adopted?
No, we haven't done that, and I think probably the main reason is that the person who presented before me talks about the certification process. So they may be like, as a researcher, you may not really care too much about what you do get certified because maybe you just want some quick and easy prototyping. So this is what that's kind of more geared for.
Great, great. All right, I think let's thank the speaker again.
Thank you.
For the third speaker here. Go ahead. Yeah. Could you first introduce yourself?
Okay. Oh. Okay. Hello. My name is Yuta Shimamoto from Okayama University, Japan, and I'm going to talk about our work in progress research titled Runtime Consistency Enforcement between SBOM and Software Execution. So first, I'm going to talk about what is SBOM. SBOM is a formal machine-readable metadata that lists software components, which enables consistent sharing of component information across the software supply chain. One example of create SBOM is for IoT devices, and in the Cyber Resilience Act, it says that it must provide that. And IoT software composition is difficult to understand quickly and accurately because it has a huge number of components in the IoT firmware. For example, about home router firmware, there is 662 components in average. And SBOM improves visibility into system composition through a list of software components and address the program. And it is useful for faster vulnerability management and incident response. However, SBOMs do not always comprehensively or accurately reflect the actual composition. And one example of that is the software or firmware update. So if you have a firmware and the SBOM of that firmware, and if you update the firmware, but doesn't update the SBOM and continue to use, that SBOM will be outdated and it has inconsistencies. Those inconsistencies have a risk of executing programs not listed in the SBOM, which indicates that unmanaged programs are running, and that may lead to missed vulnerabilities based on the SBOM of the vulnerability management. Therefore, it should ensure that only SBOM-list program will be executed. One way to do the execution control is to use the mandatory access control, or we say MAC for short. This enforces access control based on predefined security policies and managed and configured by the administrations. I mean, the policy is managed and configured by the system administrations. So even if the owner of the file permits execution, it can be denied according to that security policies. However, there is a limitation of existing Mac systems for SBOM-driven access control. One reason is that existing Mac system already has the policy, so it may be a conflict between the SBOM-driven policies and those existing policies. So it is difficult to coexist. Another reason is that SBOM-driven access control needs to enforce policy based on runtime program metadata, but existing Mac system doesn't have those functionalities. Therefore, a new method is required to verify consistency between SBOM list composition and the actual system state. And that's why we propose the SBOM-based action control, SBOM-AC. Before runtime, the SBOM is converted to the policy. The policy has an execution allow list, which is an information list of the files, which is related to the components written in the SBOM. And during runtime, we have an SBOM-driven Mac system that checks the policy and accepts SBOM-less program to be executed or audit deny execution of mismatched program in each execution attempt. Those mismatches include non-lit files and modified files. And the mismatched programs information are output as the audit deny logs. So this is the overview of the SBOM AC. To convert the SBOM to the policy, we use the SBOM to policy converter. And for the SBOM Mac system, we have a policy decision point, PDP, and policy enforcement point, PEP. So in each execution request, the PEP consults the PDP whether to do that execution request or accept or denied. And based on that decision, the PEP executes or prohibits the executes and output the mismatches. SBOM AC needs to ensure consistency between the SBOM and the executed software. Therefore, the policy needs to compare, we need to compare the policy against the latest program metadata during runtime. Therefore, in the policy, it doesn't have information that what file is acceptable or deniable, but the information of the files that can be identified the specific program. So the policy information for each entry is file path, file hash, and hash algorithm. And SBOM SC must guarantee reliable execution of SSO device services, which means SSO program must not be blocked. To do this, SBOM has two modes, audit mode and deny mode. Audit mode doesn't block the execution, but only logs all the mismatches. Deny mode prohibits the execution and logs those blocked programs. By doing this, during product development, the audit mode enables comprehensive logging of execution inconsistencies to assess the SBOM manager to refining the SBOM entries. And after product released, by using the refined SBOM, it will block the deny mode will block the suspicious program execution and also don't interrupt the SSO device services. As I said, SBOM manager can refine SBOM entries during development. This does not only prevent the disruption of SSO operations in deny mode, but also strengthens the effectiveness of SBOM-based vulnerability management. Also, security analysis can analyze log programs and taking appropriate countermeasures. And yeah, this is all about the SBOM AC. So to do the verification of the core functions and evaluate the latency, we made the prototype of the SBOM AC. And the prototype has two components. The policy loader simplified SBOM to policy is a simplified version of the SBOM to policy converter, and the execution enforcer provides PEP and PDP functionalities. Note that the policy loader, the SBOM, needs to include file path and the file hash values strict to SHA-256 to convert by the policy loader. And the controllable program needs to be in the specific directory. So about the verification, we verify 3 core functions, which is permitting execution of SON-less programs, denying non-complement programs, and recording all the deny logs. As a result, all core functions were successfully verified. And next is about the latency evaluation. We do this to estimate the runtime impact. So we measure the execution time on the light rate string output program by 3 SBOM AC conditions and 2 SBOM entries. And the SBOM AC conditions are SBOM AC disabled and SBOM AC enabled by allowed execution and SBOM AC enabled with denied execution. And about the SBOM entries, we have one entry that is include only the the program that is used for the evaluation, and the second is that 475,955 entry, which includes non-evaluated files. For each condition and entry code, we average the execution time over 100,000 runs, and we repeated those averaging process 100 times and check the maximum, average, and minimum of those averages execution time. SBOM AC was fixed to audit mode because deny mode cannot be directly compared with the SBOM AC disabled baseline, so it cannot calculate the latency of the SBOM AC. So this is a result of the evaluation. We can see that comparing by SBOM entries, it has only denied execution if there's a slight increase. And comparing by SBOM AC conditions, we can see that the minimum time on the SBOM AC disabled is 2.39 milliseconds, and the maximum of SBOM AC enabled is 2.53 milliseconds. So we can say that SBOM AC has a maximum of 0.14 milliseconds to execution time. Therefore, the resulting runtime overhead and thus the performance impact is expected to be negligible. So for the conclusion, because that SBOM AC may contain errors, inconsistencies, we propose SBOM-based access control, which ensures consistency between the SBOM and the executed software. And we implement the prototype and evaluate it. All function was verified on the Linux-based system, and the runtime overhead is expected to be negligible. And yeah, that's all. Thank you for listening.
Great. Let's thank the speaker. Any question from the audience?
Thank you very much. Really good speech. Can I ask, do you plan to take this to manufacturers? Is that an end goal once your research is complete in this area?
Yes, we are planning to make that as a, we are now considering that to do to the manufacturer or not, but yeah, that's one pattern of the goal.
Great. I think we can leave more questions to the poster session following this session before the lunch break. So let's thank the speaker again and welcome the fourth speaker.
Okay, thank you. My name is Maximilian Eichhorn. I'm from the FAU, and I would like to talk about our paper, UDIM Formal User-Device Interaction Model for Approximating Artifact Coverage in IoT Forensics. First of all, to start with a little bit of motivation why we need a model. We already heard about it. We have a lot of IoT devices, and nowadays they are everywhere. And these IoT devices differ vastly, not only in hardware, but also in software and form factors. Because they are nearly everywhere, we have a lot of potential sources of digital evidence or security risks. And because they differ so vastly, it is not that easy to compare forensic results across IoT devices. And then we even have the problem that we have different examination methodologies like differential forensic analysis or scenario-based analysis, and therefore the results and the depths of the results vary vastly. Yeah, we have a completeness of, we have the problem that a completeness of forensic examinations is often unclear. And in this gap, we want to put our model forward, and we come across the idea to design a user-device interaction model. On the slide, we have a graphical representation of the model, and we walk through the different components of the model in the next slide. Our model is device-centric, therefore we first talk about the device itself. We defined our device as a computing system that has digital storage to not only store the firmware or the operating system, which is necessary to provide the device functionality, but also usage data. And every device has its environment. We define the environment of a device as the spatial surroundings of the device with which it can interact. These interactions can be via acoustic, visual, or other sensory measurable means. And such environments can include other devices or users. Now we have the foundation to talk about the formalization of the model in general. We define our model as dependent on the device and its environment as a graph with a set of nodes and a set of edges. The device itself is obviously in the set of nodes, and we have one edge from the device to the device itself. And about this edge we will talk later on in more detail. That's the foundation of our model. But our graph not only consists, our model consists not only of one graph, we have 3 subgraphs defined regarding the location in relation to the device itself. First, we have the proximity subgraph. This subgraph contains all nodes which are in the same environment of D, obviously including D, and that's only to talk about the location in regard of the device from the environmental perspective. When we talk about the protocols, the network perspective, we talk about the internal network subgraph. This subgraph includes all nodes located in the same network as the device D, obviously also including D, and it is irrelevant if this network is, on which protocol this network is based. It can be Bluetooth, Zigbee, Wi-Fi, and so on and so forth. And lastly, we have the external network. In this network, we have all nodes which are not in the same network as the device, but can interact with it. In the, most of the time, we have cloud servers and remote access from users to the device in this subgraph. And that concludes the 3 subgraphs. And now we can talk about the interactions. We have in a graph different passes. In each pass is a sequence of nodes, and when the device is the starting or ending node of such a pass, we call it an interaction. And all nodes contained in the interaction are called the interaction participants. In this example, we have marked the interaction between a device and the other device of the same environment. And as already mentioned before, we have a special interaction from the device to itself, which we call a device internal interaction. For example, when on the device there is a local mail client and a local web server, and when these applications interact with each other, then we have a device internal interaction between two applications of the device. Then we have additional interaction types which we will define, and therefore we look at the length of the path and define 3 different types regarding on the length. First, we have the classical user-device interaction as a direct interaction. That could be when there is a keyboard directly connected to the device and the user is typing on this keyboard. We have a direct interaction and no steps in between. But not all devices have these input types. Some devices you can only interact with the companion app, and therefore you have a state in between, a step in between, in this case the phone where the companion app of the device is running. We call this a single step transitive interaction, and as you can see on the bottom, we not only have the cases where we only have one step in between. There are cases with more than one step in between. For example, when you can't access the device directly, when you have always to go over the cloud servers of the device and the companion app, then you have a multi-step transitive interaction where the user performs the interaction via the companion app, the cloud servers, and then to the device. And it is necessary to differentiate between these interaction types, because when you look for digital forensic traces of these interactions, you can look on the device itself, but when you have an interaction which has steps in between, you can also look onto these steps in between if you find artifacts of these interactions. When we applied our UDIM, we got this interesting table on the right side. It is a little bit small, you probably can't read it, therefore you just can visit me after this session at my poster, and then I can show you the table in a little bit more detail. We applied our UDIM to 42 devices from 24 different sources. And we applied it to sources from different types, academic papers, blog articles, and even data sheets. And with this application of the UDIM, we could identify examination gaps. And when you want a little bit more information to these gaps, you also can come forward afterwards to the poster, and then I will talk happily about these gaps. But to look into the application with a little bit of an example, we look onto the first line of the table where we have the device Thermomix. It's a kitchen application, and we apply the UDIM with this device as an example in the following slides. Yeah, it's a kitchen application, and as you can see here, we have a picture in the kitchen to identify the different interaction participants. Because our model is device-centric, we first have our device, the Thermomix device, and we not only need the device, but we can look into it with what interaction participants we could interact. Each device has its environment. In this case, the device has a speaker and therefore can interact with the environment via the speaker, giving sound output, which can then be detected by other devices like the small IP camera on top of the cupboard. Therefore, we have the environment. But we not only have the environment, we even have a user. In this case, the user can directly interact with the device via a rotary knob or a touch screen. And the user even has a phone in his hand. We have the next interaction participant, which we have to look into. And lastly, the device has Wi-Fi connectivity, and therefore we also have to identify the Wi-Fi router as interaction participant. When we then formalize these example participants, we get the complete graph of the device, of the Thermomix device, where we have these three subgraphs: proximity, internal network, and external network. In the proximity, we have the device itself, the user for the direct user-device interaction, and the environment. In the internal network, we obviously have the Wi-Fi router, and the user with the phone where a companion app is running. Yes, and the Wi-Fi router is not only in the internal network, but in the external network. And in the external network, we have some general server connections like DNS server, NTP server, but we also have a connection to the device-specific cookie-door server. It is a server it's a server with a recipe platform where you can download recipes to the kitchen device and then hopefully cook these recipes as expected. And you not only can download recipes from the device with the device from these cookie door servers, but you also can interact with the cookie door server over the companion app, and therefore influence the recipes downloaded on the device. And that's the reason we have the user again in the external network with the companion app again. To conclude the talk, I want to talk about the takeaways and the future work. Our UDIM provides a formal device-centric model which systematically captures all device interactions across all the locations and interaction types. Furthermore, it approximates the artifact coverage to identify examination gaps, and it has two different practical values for law enforcement. First, the law enforcement can prioritize seizures regarding the interaction types. When you want to only confirm an alibi, then you would have to look for devices with direct user-device interactions. And it is also possible to map investigative questions to specific interaction types, as I did before. When you want to talk about the alibi, then you want to answer the question if the person was present at the place, and therefore direct user-device interactions are the way to go. For future work, it would be nice to create a knowledge base applying the UDIM, basically the table to put the table to use and store these informations, whether interactions are possible, whether there are forensic artifacts of these interactions, and then law enforcement could use such a knowledge base to prioritize seizures for devices. And furthermore, we would like to encourage the inclusion of UDIM graphs in future publications to get a gist what the device has as interaction participants, and then you can look if the examination was complete or some participants were missing. And it would be interesting to integrate the UDIM into forensic tooling and investigation workflows. Thank you for your attendance, and now I'm happy to answer all questions from the audience or later on in the poster session.
Great, let's thank the speaker. Also, let's leave the question to the poster session and to save time. In the sake of the, yeah, okay. The fifth speaker, are you ready?
I'm a little confused. Is that what will be shown on the big screens?
The IT, yeah, it's showing there.
Okay, I see. All right.
Could you first introduce yourself?
Sure. Yeah. All right. Hello, everyone. I'm David. I'm a PhD student at Fraunhofer University in Germany. Basically, I would like to talk to you about my short paper identifying microcontroller architecture through static analysis of firmware binaries. Or in other words, what device do I need to emulate to run this particular firmware binary? So let's first start with some motivation. Firstly, I don't need to tell you this, but embedded devices are often used to process sensitive information or have safety implications beyond what you would expect from usual software applied by user. An example I like to use is a smoke detector. If a smoke detector malfunctions, you have an entirely different set of problems than if your email client crashes. So it's really important that these devices are not that easy to exploit. However, especially for cheap devices, the vendor support can be limited. You often can't expect the vendors to thoroughly check their own firmware for vulnerabilities or to provide firmware updates in a timely fashion, which makes third-party analysis essential in some cases. However, firmware is less amenable to analysis than other software. This is largely due to hardware constraints and optimization pressure in the manufacture and development of the embedded devices. What you often see is that you have no operating system abstraction at all. You have hardly any legible hardware abstraction in your firmware binary. The firmware binaries are often distributed without any debug symbols. And overall, you just have to work with very limited information about what hardware the firmware expects to run on. So why is this a problem? To answer that question, let us look at the three main ways of how firmware analysis takes place. One way is static analysis. This involves decompiling a firmware binary, then you do some reverse engineering on the decompiled binary or some data flow analysis. In both cases, you want to know through which interfaces data can enter and leave the system. And to know that, you need information about the hardware, which it expects to run on. Then you have on-device fuzzing. This involves executing the firmware on its native device and sending in test cases until it crashes. For efficiency, you will usually want to patch a fuzzing harness into the firmware, which of course requires you to know what hardware it runs on. And then lastly, you have rehosting, which involves running the firmware in an applicable emulator. Since firmware often runs on exactly one kind of device, it is important that the emulator matches that device. Sometimes you even have to implement your own emulator to do it. And of course, that's much easier if you have hardware information. So the main message is whatever you're trying to do in firmware analysis, knowing what hardware it runs on will be helpful. So what kind of information do you need? The main component of any embedded device is its microcontroller unit or its MCU. It's located somewhere in the board and looks like this, or like this. All pretty similar, black chips with some writing on them. It contains the CPU and a lot of peripheral devices, and all in all, it defines the address space that the firmware will run in. Usually, when you know what MCU you have, you can just Google the reference manual online. It's usually a large PDF document, very comprehensive, describes every single peripheral in the address space. Right. So how do you find out what MCU you have? The usual approaches are these steps. First, you purchase the device, then you open it, then you inspect the device to find where the MCU is on the board, and then you read the tiny numbers written on it, and then you Google for them. Of course, you can't do this at scale. So imagine you have a couple dozen of firmware binaries and you want to analyze them. You won't go to the store and buy every device. That's just not feasible. So what my approach tries to do is to get this information directly from the binary. You don't have to follow any of the steps above, and you basically don't need any access to the device at all. So this is the high-level overview of the approach. What you can see here, can I do some kind of pointer? Yeah, like this. So what you see here is the internet. We search the internet for as many descriptions of the MCUs as possible and collect them in the knowledge base and memory maps. Then down here you have the firmware binary we are trying to analyze. We perform some static analysis on the binary to collect a map of the memory accesses the firmware attempts to perform. And then you compare this memory access map to every single memory map in the knowledge base and find the most similar memory map. And ideally, that memory map corresponds to the MCU that the firmware would run on. Yeah, let's go in a bit more detail. So remember these reference manuals from before. Many vendors provide a machine-readable version of them. They look like this. They are called SVD files. It's just a very large XML document containing a lot of information. As you can see, it also contains some irrelevant information bars, such as interrupts implemented by this peripheral in question. It contains some human-readable names of devices. It contains some human-readable descriptions. We don't care about most of the stuff in the SVD. We only care about the addresses. So what we do in the next step is we simplify. We create what we call a shadow map of the memory map. This is basically just two large lists of integers, one containing every readable address and one containing every writable address on the specific MCU. And this allows us to reduce the size of the knowledge base to to less than 200 megabytes. Okay, so now that we have a knowledge base, we can begin analyzing our binary. So we load our binary into Ghidra, and we use it to decompile the binary and to find all the addresses it attempts to read from or write to. And finally, we create what we call an access map, which is pretty similar to a shadow map. It's just the same two lists of integers, one for every address the firmware attempts to access. Right. Finally, we use our access map to compare it to every single memory map. We use the Jakarta index as the similarity metric. And to the right, you see the output of our tool. So what we can see here is a ranking of memory maps by their similarity to the access map of the firmware binary we are analyzing. And what you can see here in particular is that the analyzed firmware binary is probably for Raspberry Pi 2040, if it's big enough. It might also be for this other Raspberry Pi, but it's probably not one of these devices. We know this because the normalized scores of them, which you can see over here, are way smaller than the similarity scores of the Raspberry Pis. And how does our approach work? We try to evaluate this question in 5 sub-questions. So firstly, we looked at the question of how many of the MCUs are contained in the public repositories and how many of them can be distinguished solely by their shadow map. So this is just an analysis of the repositories without any actual devices compared to them. We found that no matter the size of the repository for the 2 largest repositories, about 42% of the devices have unique memory maps, while the other larger half is just duplicates of the memory maps that we have in the smaller part. So we already see the approach won't work perfectly, but we do have some variation in memory layouts. Then we ask ourselves how likely is the target MCU of any particular firmware image to be represented in this knowledge base. So we collected 53 firmware binaries from different sources, and we found that for 68% of them, the firmware binary itself was present in the knowledge base, and for 81% of them, some device of the same MCU series was included. the next question, we evaluated how often our approach actually identifies the target MCU firmware image, and we found that for 44% of them we could identify the precise correct MCU, and for 59% of them we identified the MCU was in the top 3 results. And then the next question, we evaluated just the MCU series. So this figure is actually more important than the one before, because often all devices that belong to the same MCU series share a reference manual and have pretty much the same memory layout. So if you find an emulator that works for one of them, you found one that works for all of them. So what we tried to do here was to just see if we can identify the correct MCU series using our approach, and we found that in most cases we can, and in the top 3 cases, and in 67% of the cases, the correct series was in the top 3 results. Now, finally, we evaluated how whether changing the composition of our knowledge base affects the accuracy of our approach. Yeah, and basically what we found was that having a larger knowledge base is not always what you want. Sometimes adding memory maps to your knowledge base can produce incorrect results. In particular, we found that small memory maps tend to score unreasonably high if they have any matches at all. And we also had issues with accesses to volatile memory being misinterpreted as peripheral accesses, which also led to false positive results. There is a more in-depth case study on this. Just ask me about this later if you want to, or you can read about it in the paper. So I thank you all for your attention. You can get the paper and the tools presented at this short URL, or as I said, just ask me later.
Any questions from the audience?
Hi, thank you for your presentation. That's quite impressive. I wonder, because like this SVD is kind of standard, it only based on like ARM, but there's other architectures in the MCUs like MIPS or RISC-V. How do you cope with that?
So for this paper, we limited ourselves to Cortex-M processors. So it's basically all ARM. As far as I know, there aren't really large knowledge bases of memory maps for other architectures. So that was the one limiting factor. On the other hand, really most devices, or actually every single device I physically inspected had an ARM processor inside. So I don't think that's such a huge limitation.
Yeah. And I have another question about, because the accuracy rate is not that high, and which means like the identification, this process is not that precise enough. And have you considered use like dynamic analysis to just try to identify different binaries?
That's actually a reasonable next step. So what I was thinking about, there are emulators like Fuzzware that basically run your binary and at runtime look at all the memory accesses and try to identify what kind of peripheral you have. And this could be another way to create the access map, which would probably be a lot more precise than the way here, present here.
Cool. Thank you.
Great. For the sake of the time, and let's conclude this session. And let's thank the speaker again.